125 pounds, and we'd have this curve, and notice, theoretically, we'd never ever have 0 pounds. But actually what would happen is over many thousands of years, the material would be reduced to just molecules of this radioactive material. Excuse me. This is quite important, this notion of half-life, because, for example, because of radioactive waste from nuclear power plants, and I assume also from nuclear weapons that were needed for the Cold War, we have a stockpile of radioactive waste material. If this material, for example, has a half-life of 100 years, 300 years from now, there'd still be 125 pounds of that radioactive stuff left for every 1,000 pounds we have today. And quite frankly, some of the radioactive waste we have, I believe, has a half-life much greater than 1,000 years. Much greater than 100 years, in fact, as much as 1,000 years. So that that's something to seriously consider when we consider our Earth and the ecology therein in terms of waste matter that's radioactive. And again, all this is based on the notion of the exponential function, just like the one we looked at. Okay. Now, we want to look at one more, because one thing we haven't done is we haven't looked at what happens if the coefficient, that a in ab to the x power, is a negative number. Let's look at the next visual, which shows us y equals negative 2 to the x. Notice that negative is in front of the 2 and is not in parentheses. So again, we're multiplying by a negative after we raise x to a power. And look at the graph. The graph in white was the original graph we did, y equals 2 to the x. The graph in blue is the graph of y equals negative 2 to the x. Notice what we've done. In fact, anytime we multiply a function by a negative, all we do is reflect it, or if you like, flip it around the x-axis. So certainly y equals negative 2 to the x would be a great function to use if we had something that was decreasing, and initially decreasing very slowly, and all of a sudden was decreasing very rapidly. This possibly could be something, for example, like what happens to a stock when people start to sell it. The price goes down, and people hear this, the price is going down, so they sell it. And the price goes down more because there are fewer people buying and more people selling. And as the price goes down more, people panic, and pretty soon everybody wants to sell their stock, and since people aren't interested in buying it, they've got to lower their price drastically, and the people who sell it at the very end of this period wind up losing a great deal of money, because what you have is an exponential situation, very similar to perhaps to this y equals negative 2 to the x. Okay, I think we've had a pretty good look at exponential functions in terms of graphs. You'll see more of this in later courses for sure. But let's take a look at solving some of these exponential equations. Let's go to the board and take a look at a typical exponential equation. So we'll erase our half-life graph. And let's take a look at an equation like this. There is an exponential equation. Equation and the exponent contains a variable. Very important. That's what an exponential equation should look like. Well, basically, the way I like to solve exponential equations at this point in time is to get both terms on both sides of the equals to have the same base. That is, we need to make 81 a power of 3. Is 81 a power of 3? Well, let's see. 3 squared is 9, 3 cubed is 27, 3 to the 4th power is 81. How nice. Well, of course, if this had been 3 to the x equals 72, you couldn't have done it right now. The next lesson will give us some hints at how to do that, but we're not up to the next lesson yet. We're still talking about solving these exponentially. So, 3 to the 4th. Now, let me ask you a very, very simple question. Two numbers are equal. They have the same base. What do you know about the power? What you should say is that the powers have to be the same, because you couldn't have 3 to the 4th and 3 to, let's say, the 5th be the same number. That's silly. It couldn't be. So if 3 to the x and 3 to the fourth are equal, and 3, of course, is equal to 3, then x must equal 4. And guess what? We're back to a very simple linear equation. In fact, the simplest linear equation. If x equals 4, what does x equal? X equals 4. And we can check that. 3 to the fourth, indeed, is 81. So we solve the exponential equations by getting both sides of equals to have something that has the same base. And then we set the power as equal. And we wind up generally with a linear or possibly a quadratic equation, something we know how to solve. So let's look at the next visual. The next visual shows us the equation 8 to the 2x equals 16 to the x plus 1. This is a bit different because we don't have the same base. So you could say, well, I guess we can't do this. Well, let's stop for a second. I wouldn't be giving you this problem if we couldn't do it. The question is not that we have to be able to make 16 as a power of 8, but we've got to get both terms having the same base. That is 8 a power of a number that 16 is also a power of that number too? And as you can see in the second line, which is highlighted, 8 and 16 are both powers of 2. So we have 2 to the third in parentheses, that's 8, raised to the 2x power. And on the other side of equals, we have 2 to the fourth in parentheses, that's 16, raised to the x plus 1 power. Now we use the rule we talked about earlier. When you raise a base to a power, you multiply the powers. So on the third line, which is highlighted, we see 2 to the 6x equals 2 to the 4x plus 4. We've multiplied x and plus 1 by 4 to get 4x plus 4. Now we have an equation equals, the bases are the same, and therefore we set the powers equal to each other, which is exactly what we'll do in the next visual. We have 6x equals 4x plus 4, and we're back to a simple linear equation. We subtract 4x from both sides, we get x equals 2. We're not done, we need to check. We go back to the original equation, 8 to the 2x. Well, if x is 2, 2x is 4. So 8 to the 4 must equal 16 to the to the x plus 1. X is 2, 2 plus 1, indeed, yes, that's right, x, it's 3. So is 8 to the fourth equal to 16 to the third? Most of you probably don't walk around knowing your powers of 8 and powers of 16. A good use of a simple calculator. 8 to the fourth is 4,096. 16 to the third is also 4,096. Our equation checks. The answer is x equals 2. Okay, let's take a look at the next visual. Now, what is different about this equation? You'll notice that on one side we have a 9 to a power. On the other side we have a fraction, 1/27th, raised to a power. That's a bit different, but this is still an exponential equation because it's equals and the variable is found in the exponent. What do? Well, as shown, we need to get both bases the same. Well, we look and see, I say 9, I know is a power of 9. It's also a power of 3. The fact that it's a fraction, 1/27th, we don't worry about. We know that it's a reciprocal, and reciprocals are simply negative powers. So the question is 27 a power of 9? And the answer is, it is not. It is not a power of 9. Is it a power of 3? Yes, 27 is a power of 3. In fact, it's 3 to the third. Well, if 27 is 3 to the third, we should know that 1 over 27 is 3 to the negative third power, the reciprocal of 27. And thus, we've changed the 9 in parentheses to 3 to the second. We've changed the 1/27th in parentheses to 3 to the negative third. And now we use exactly what we did in the previous problem. We multiply, because raising a base to a power, you multiply the powers, and we get 3 to the 2x plus 2 equals 3 to the negative 3x plus 9. Now we're back in the situation. We have an equation, equal bases. We set the powers equal to each other, and that's what we've done in the next visual. We have 2x plus 2 equals negative 3x plus 9. We, again, we're back to where we were many, many lessons ago, solving a simple linear equation. We want to get the x on one side, so we add 3x to both sides. We subtract 2 from both sides to get the number term on the other side. We have 5x equals 7, and we get x equals 7/5. This leads to an interesting check because 7/5 is a fraction. And by the way, we go back into our original problem, 9 to the x plus 1. Well, x plus 1, if x is 7/5, that would be what? That would be 12/5. And 9 to the 12/5 means take the 5th root of 9 and raise it to the 12th power. I don't think you can do that in your head, and probably using your fingers won't help. Again, we call for the calculator. I took a calculator and raised 9 to the 12/5 power, and I got a number that was 195.0661995 ... because it's not a precise number. This is close enough. Okay? Then I did the same thing. We said, let's see, -3, we have 1/27 to the x minus 3. We replace x with 7/5, and 7/5 minus 3. So I raised 1/27 to that power and got 195.0661995 ... So the two answers, the left side and the right side of this equation, when we plug in x equals 7/5, are precisely the same. And therefore it checks. And the interesting thing about the check is we got this crazy number with all these decimal places in it because we were dealing with, in effect, irrational terms because of the 5th root business. But the fact is, using a calculator has helped us to check to see that for our original equation, the only answer that works is x equals 7/5. All right, what have we done? We've looked at the meaning of exponential functions and the use of exponential functions. We've seen how to graph exponential functions by plotting points and looking at the typical kind of exponential function. We have also looked at exponential equations and how to solve them by simply getting both terms on the left and the right to the same base, set the powers equal, and solve the equation that results. In the next lesson, lesson 25, we will take what we've learned here and expand it by using logarithms and investigating logarithm functions. What's a logarithm? You'll find out in the next lesson.